Okay, well, thank you very much for the invitation to Andreas and to the Institute for the opportunity to come and speak to you. The variational bicomplex is a subject that's very dear to me. I've spent a lot of time working on it over the years, and it's a pleasure to be able to revisit some of these topics and talk about some new things as well. So I'm going to give two lectures. The first one, I start with a very gentle beginning with a little bit of review of calculus of variations. Then we'll spend the most of the day today talking about what's called the free or unconstrained variational bicomplex. And I want to focus on, this is the main topic for today, what's called the first variational formula. And I want to give a global version of this formula and show how you derive this formula using some of the machinery from the variational bicomplex. For my second lecture, which is tomorrow, I'll just make a few historical remarks. I'll talk a little bit about generalizations of this free variational bicomplex, the variational bicomplex constrained for differential equations, the variational bicomplex for, in the case of symmetry groups, so invariant variational bicomplex. And then there's so many applications of this that I wanted to just kind of give an overview of lots of different applications. I picked quite a bunch, and in fact, the audience or people in the audience can say, well, can choose which ones they want to hear about a little bit if there's something of particular interest to some people. Okay, so let's begin at the very beginning with the simplest problem in the calculus of variations. So we'll start off with the XY plane. And we're going to look at a curve. We have two fixed points, a point here and a point here. And we're going to look at curves which are joining those 2 points. So the x-coordinate is A, and this x-coordinate here is B. And we want to look at the following functional on curves. It's the integral from A to B of some expression involving the independent variable x, the dependent variable y, and its first derivative. And the problem, as I think many people know, is to find those curves joining these 2 points which minimize this. In the physics is called the action integral. In calculus variations, this is sometimes called the fundamental integral. And the goal is to minimize I relative to all nearby curves. I said nearby because exactly what that means might depend upon what function space you set up in order to study this problem. That's not going to be of interest to us. What's interest to us is how this, how you begin to solve this problem. So the first thing you do is you pick another curve H, and I'm just going to draw it in like this. And this curve is to be viewed as a deformation of the original curve. If we were doing what's called the fixed endpoint problem, then we'd want our curve H to be zero at the endpoints. But this is my deformation, and this is what I've called y sub epsilon. Okay. And then we're just going to use elementary calculus to now view this expression I of y as a function of epsilon. And then we use the standard test for a minimum that the derivative of a function of epsilon should be equal to 0 if we're at a critical point. So here's our function of epsilon. It's this expression right here. It's the Lagrangian evaluated at our moved curve or deformed curve. And we have to differentiate this with respect to epsilon. Well, there's never much problem bringing the derivative with respect to epsilon underneath the integral sign. Then you're going to have the derivative of L with respect to this slot, y, times the derivative of y epsilon, which is h, and then the derivative of L with respect to this slot, which is this slot's called y prime, times the derivative of the deformation h. Okay, and so you have this expression right here for the derivative. And this has to be 0. We want this to be 0 for all h's. Okay. Now, at this point, just for the moment, I want to be a little bit careful and show you what can come up if you're being careful in the calculus of variations. Well, we should say a little bit about the degrees of differentiability of this problem. So I'm looking at this Lagrangian, and it's a function of 3 variables, and a standard assumption would be to assume that this Lagrangian is of class C1. Secondly, in order to calculate this integral, I should assume that y is of class C1, so this function here would be continuous, and this whole integrand would be continuous. Maybe I'll allow for piecewise C1. But the point I want to make, just by way of this introductory remarks, is that if we're being very careful in the calculus of variations, all we would know about this is that this is continuous and this is continuous. So the normal procedure of integrating by parts not going to work exactly correctly, not going to work for you. It doesn't matter, because if we look in Gilfan and Fefferman, if you're not too familiar with the calculus of variations, this is a terrific book, and I highly recommend. It's got lots of good stuff in it that you don't find in other books, and it's a really great introduction to the calculus of variations. The book's called The Calculus of Variations, and in that book you'll find a lemma, and the lemma says the following: suppose you have an expression of the form integral from a to b. Alpha of x times h of x plus beta of x times h prime of x, where alpha and beta are just continuous functions, and h is a differentiable function. If this is 0 for all h, then a miracle happens. This condition forces this derivative to be of class C1, and you get alpha of x has to equal beta prime of x. So this is sort of like this is what you get, which is essentially the Euler-Lagrange equations, without making high demands on your differentiability. If, however, and this is the case that we'll talk about mainly, the Lagrangian and our minimizing function are of class C2, then we can integrate by parts. This is a standard trick in the calculus of variations. So write this as the total derivative of this expression minus derivative of this term times h. Left out the h there. Okay, and so this is the formula that I'm trying to get to. The derivative for our fundamental integral, our action integral, is given by this expression right here, integrated against h. This is called the Euler-Lagrange operator for L. And then you have this term left over coming from right here, this term right here. And that's an x derivative, so you can integrate out, you can do the integral and just get this term evaluated at the boundary. So here's the first variational formula in the calculus of variations. It consists of this term right here. I left out the h of x again. Involving the Euler-Lagrange equation and this boundary term. If we're doing the simplest problem of the calculus of variations, where we want to only do variations which preserve, so our family of curves that we're looking at all preserve, all start and end at the same place, then h of a is 0, h of b is 0, and this term is not present. In Gilfan and Fefferman, they look at cases where the endpoints are allowed to vary along a curve, or they look at the case where your extremals are only piecewise differentiable. And in those cases, this boundary term, which is not present in the simplest problem in the calculus of variations, becomes present. And one of the themes for today's lecture is that the Euler-Lagrange operator is very, very important, But this boundary term, which isn't present in the simplest derivations, is also very important in all kinds of questions in calculus of variations and in differential geometry in general. So there's a quick introduction to calculus of variations. You counter right away an expression which is called total derivatives. So we say that the Lagrangian x, y of y prime is a total derivative if there's a function depending only upon x and y such that L is the total derivative of f. So writing that out, that would be df dx plus df dy times y prime. We call this the total derivative because you have to differentiate y as a function of x. So in this case, something happens. For Lagrangians, which are total derivatives, we can of course evaluate the fundamental integral and just get it to be a boundary term. So in this case here, if you have a total derivative operator, its variation will be a pure boundary term, no contribution to the Euler-Lagrange equations. But it's important to note that this boundary term can affect other parts of the variational formalism. The Hamiltonian, conservation laws, all of those will be adjusted if you change your Lagrangian by a total derivative. So this is a standard proposition, but in the variational calculus, L is a total derivative, so L looks like this if and only if the Euler-Lagrange expression of L is 0. Lagrangians whose Euler-Lagrange expressions are 0 are frequently called in this business null Lagrangians. So I gave a proof of this, that if you have a total derivative, then the Euler-Lagrange expression would be 0 using the action integral. But what I want to point out, I'm not going to go through all these calculations here, but you can just simply calculate, here's my L, you can just simply calculate the derivative with respect to y, the derivative with respect to y prime, plug into the Euler-Lagrange expression, and you find that the Euler-Lagrange expression equals 0. This is just like a good exercise in elementary calculus. The only thing you really need to make this work is that partial derivatives commute. So this is sort of like an integrability condition for when is L a total derivative? Well, sort of the integrability conditions for that are E of L equals 0. So conversely, if we have a Lagrangian and the Euler-Lagrange expression is identically 0, well, let me write that out. Something very interesting happens. This is an argument that gets used over and over again in the calculus of variations, so I thought I should show it just once. If I write out the Euler-Lagrange expressions and I see that the L depends upon x, y, and its first derivative, but the Euler-Lagrange expression depends upon second derivatives. So if this Euler-Lagrange expression is identically 0, then this term involving y double prime must be 0. And so that means that if I have a null Lagrangian for the simplest problem in the calculus of variations, then this condition must be true. L must be linear in second derivatives. You take this linear formula for the Lagrangian, plug it back in, you'll get a curl type condition, which says that A has to be a function, the derivative of a function with respect to x, and B has to be the derivative of a function with respect to y, and that brings you right back to this formula right here. This is a fairly typical kind of argument that appears. In more general cases, the situation is quite similar. If you have a null Lagrangian, there's very strong constraints on its algebraic form. Okay. The next thing I'd like to talk about a little bit is what's called the inverse problem in the calculus of radiations. This problem was first studied by the mathematical physicist Helmholtz back in the 1880s. And he asked the following basic question. Suppose we have a second order differential expression, so some formula involving x, y, y prime, and y double prime. And Helmholtz asked the following question: when is there a Lagrangian such that this expression T is the Euler-Lagrange expressions for this L? So we want to know when T, here's the Euler-Lagrange expressions written right out again. But we want to know, given this, when is there an L such that we have this equality? Helmholtz's idea was the following. If I have a differential equation or a system of differential equations, and I'm trying to integrate that system of differential equations, if I find a Lagrangian for it, then perhaps I can write down the Hamiltonian equations for that Lagrangian, do separation of variables on the Hamiltonian equation, on Hamilton's equation, and then get back and get my hands on solutions to the others. So his original motivation for studying the inverse problem was as an integration technique. So we have the following theorem. T is an Euler-Lagrange expression, if and only if. Well, you can see right away one of the constraints is T better be linear in second derivatives, so you better have this condition. And you have something like kind of looking a bit like a null Lagrangian condition. It's that the partial derivative of T with respect to this slot should be the total derivative of T with respect to this slot. And this condition here is called the Helmholtz condition for this differential equation. It's not difficult to generalize the Helmholtz condition to higher order ODEs and partial differential equations. Again, the proof of this condition is just an exercise in, is just a formal calculation. If T is an Euler-Lagrange equation, so the proof going in one direction, if T is equal to E of L, then you can calculate this derivative. You can calculate this derivative, and you can just see right away that you have an equality here. So again, one can view the Helmholtz condition as sort of like the integrability conditions for this problem. Going the other way, there's a very handy-dandy shortcut due to the mathematician Weinberg. So this is often called the Weinberg formula for the Lagrangian. It says the following: take your differential operator, multiply it by your independent variable, language of physics, multiply it by your field variables, and just do this very simple line integral, and you'll get a Lagrangian for the problem. So in some sense, that proves the converse. But wait, there's a little tricky business here. We started off asking when there was a first order Lagrangian, and this Weinberg formula here produces for us not a first order Lagrangian, but one that explicitly involves second derivatives. So to finish this story, what you should do is take this Weinberg Lagrangian, L. You should find some function now of one derivative, such that when you add this function to the Weinberg Lagrangian, you get a new one, but this term here matches off against the second derivative. The second derivatives in this divergence or total derivative term kill the second derivatives in the Weinberg problem, getting you to be a first order Lagrangian. So in this business of formal variational calculus, the variational bicomplex, you have to have one of two mindsets. Either the orders of the objects that you're dealing with you don't care about, you just want to know that they exist and they satisfy the conditions that you want, or you want to do a very fine, granular, detailed structure analysis and keep control of the possible jet orders of all the objects that come into play. No introduction to the calculus of variations would be complete, of course, without mentioning the famous Noether's theorem. And so let me just say a quick word about that. So let's consider a transformation. I've changed variables here on this slide. So in the previous slide.
Can I ask a question?
Sure, go ahead.
From the previous slide. So you answered if T is.
Just let me get back to that. Hold on, let me get back to that slide. Let's see. It was in the getting started here, and it was in right here. This one here.
Right. So this answers the question if T is equal to E of L. Yeah. But can one also answer if some differential equations are equivalent to some E of L, which is a more general question?
Right. So let me make a comment on that. The more general question is the following. Maybe I have to multiply f by a function to make it E of L. Or if I have a system of equations, maybe I have to have a matrix multiplier to get an E of L. Or maybe I want to, where these function matrix is invertible, or maybe I could ask for a differential operator to make E of L. So there's many variants of this. This is called the simplest problem in the simplest version of the inverse problem. In my lecture tomorrow, I'll talk a little bit about this problem in the case of ODEs.
Okay, thank you.
Okay. So this problem, the simplest problem, completely under control. This one here, much more difficult. But there is a good literature on this, which I'll talk about tomorrow, and show how one sets that problem up. Okay, so as I said, I have a little change of notation here. Going forward, x's and y's will be the independent variables, and u's and u alphas and v's will be always the field variables or the dependent variables. So let's consider a transformation, which I've indicated schematically here as a transformation of the independent variable and the dependent variable. It's kind of viewed as what's called a fiber preserving transformation. That's an important point to note, is I'm going to keep everything here as simple as possible. All what I want to say can be generalized to more general classes of transformations and very general vector fields and very general infinitesimal versions. Okay, so curves are mapped under a general transformation. Curves are mapped to curves, and if you're mapping curves to curves, then you get a mapping on their tangent vectors. And so we say that this transformation in the XU plane lifts or prolongs to a transformation involving first derivatives of the curves. At the infinitesimal level, so working with vector fields or infinitesimal transformations instead of actual finite transformations, this prolongation formula takes on a specific, a rather manageable form. This is one, I think, of Lee's great discoveries, this Lee prolongation formula for lifting vector fields in the space of independent and dependent variables up to the space of derivatives or the jet spaces. And then I simply want to take my Lagrangian and Lie differentiate it with respect to this prolonged vector field right here. And in order to Lie differentiate a form, I'll use the standard formula, hook d plus d hook. Okay, so that's the Cartan's formula for the Lie derivative. You substitute in this formula for the vector field. You write out the formula for the exterior derivative. and do some calculations, and you end up with the following formula right here. The Lie derivative is equal to some multiple of the Euler-Lagrange form plus a total derivative, and this total derivative is given by this expression right here. And in this case, I want to draw attention to this part right here. This part of our so-called conservation law, our first integral, is coming from the boundary term. Okay, this is the celebrated Noether's theorem. If we have a symmetry of the Lagrangian, then this term is equal to 0, so that on solutions of the Euler-Lagrange equations, this expression here vanishes, and we have a first integral or constant of motion for our Euler-Lagrange equations. The key here is, I'll come back to that, what the takeaway from this is in a minute. Let me do one other example. This will come up again later on. Let's look at a specific Lagrangian. So for this, I want to take a smooth closed curve in the plane. So I'm looking at a curve in the UV plane. Here's our UV plane here. And I want it to be closed, and I want it to be having a regular curve with nowhere vanishing derivative. So an immersed curve in the plane. And we don't allow the derivatives to stop, so we're not allowed to have little peaks like that. Well, given that the derivative is not equal to 0, I can define this particular Lagrangian u v double dot minus v double dot u dot over u dot squared plus v dot squared. And if we calculate the Euler-Lagrange expression of this, we get that the Euler-Lagrange expression is identically 0. And going back to our first variational formula, that says if we take our curve and we deform it a little bit to another curve, then under this deformation, this integral won't change. And so we get what is a very, very important interpretation of null Lagrangians. So for geometric problems, if we have a Lagrangian which is null, then that's sort of somehow a deformation invariant of our geometric problem. So for, of course, you might recognize this formula as the formula for the winding number of a curve. Even if you hadn't known what it is, you could calculate its Euler-Lagrange expression, see that it was 0, and immediately deduce that that expression, by virtue of the first variational formula, that this integral is a deformation invariant of the curves. Okay. Well, probably should do the same thing. Let's let K be the Gaussian curvature for a metric on the surface. Usually we see the formula for the Gaussian curvature given in terms of the coefficients of the first fundamental form and its derivatives, but there's a very big formula in Struic for the curvature written out explicitly in terms of the formula for the surface. So I'm thinking of my surface as being being given parametrically by this vector in three-dimensional space. There's a gigantic formula in Struic for what the Gaussian curvature is. Well, cheating, you know that the integral of the Gaussian curvature is a deformation invariant of the surface. So you know that if you were to calculate the Euler-Lagrange expressions for this big mess, you would get that the Gaussian curvature is a null Lagrangian. I wanted to point out that if you expand all of these determinants out in terms of minors, you'll find that this Gaussian curvature is completely expressible in terms of all the second derivative terms in the Gaussian curvature are all expressed in terms of Jacobians. And again, this is going back to some of the fine structure that you have available to you when you're studying null Lagrangians. So the fact that this is a null Lagrangian and some general theory about null Lagrangians predicts for you the algebraic structure of what K can look like at highest order derivatives. Okay, so here's the summary. We have the beginnings of what will be an important exact sequence. And the exact sequence starts with a function, and you make a Lagrangian out of that function by taking its total derivative. Then you have a Lagrangian, and if you have a Lagrangian, you calculate its Euler-Lagrange expression, and you get a differential operator T. If you have a differential operator T, you can calculate its Helmholtz conditions, and this sequence, functions, Lagrangians, operators, is exact. F goes to E of F is 0. L goes to H of E of L is 0. So we have even in the simplest problem in the calculus of variations, we have this little exact sequence arising, and that's one of the things that we're going to try and generalize today. The second thing that I want to point out is that all the operators in this complex, divergence operator, Euler-Lagrange operator, and the Helmholtz operator, are what are called natural differential operators. They have exactly the same status as the exterior derivative operator in differential geometry. They can have coordinate, they should have coordinate-free definitions. They all commute, put another way, these all commute with Lie derivatives of the prolongation of arbitrary vector fields. The third conclusion from our little introduction is that the Lie derivative of a Lagrangian look very much like the Cartan form for Lie derivatives of differential forms. The Lie derivative of the Lagrangian became hook, an interior product of the Euler-Lagrange operator. So we're calculating the Lie derivative of an object in the middle of our little exact sequence. And it became kind of a hook operator on the next operator in our sequence, the Euler-Lagrange operator. So it's hook Euler-Lagrange plus hook total derivative. So then it becomes a hook, the total derivative of, which is the operator at this level of our sequence. So a good exercise, especially if you're a beginner, is to maybe try and repeat the steps that I've talked about in this little introduction for a second order Lagrangian, or repeat it for a first order Lagrangian, but with two independent variables. So this would be the Euler-Lagrange equations in this case would be fourth order. The Euler-Lagrange equations in this case here would be a partial differential equation in two independent variables. Okay. Let's see where are we here. Okay, so that's the end of the little warm-up story. Kind of set the stage for what we want to do. It's the variational bicomplex is a double complex of differential forms on the infinite jet bundle, a fibered manifold. It gives a very effective variational calculus for studying variational principles, symmetries, conservation laws, Hamiltonian operators. The edge of the variational bicomplex gives a generalization of our little exact sequence that we've been studying. The cohomology of the variational bicomplex is readily computed. From the cohomology, you get a global first order variational formula. You get various versions of Noether's theorem. And then after that, you can start modifying this so-called free variational bicomplex to study conservation laws for differential equations. And also you have a general framework for looking at characteristic classes. Okay. Okay, so I don't want to spend too much time talking about jet spaces and jet bundles, but we're going to be using these words all the time and what follows, so we need to make a little stab at it. So we want to begin with a fibered manifold. So fiber bundle, vector bundle, perfectly good. A section, as always, is a mapping from the base space up into the total space, which projects back down. If I use coordinates xi on the base, I'll have coordinates xi and u alpha for the total space. And then sections are just maps xi equals xi and u equals some functions of the x's. Then a standard construction for this fibered manifold is to look at the bundle of jets of local sections. These are equivalence classes of local sections. Two sections defined in the neighborhood of a point are called equivalent if their coordinate derivatives, if the coordinate derivatives of S1 and S2 agree to some order K. So that's a big mouthful of words. Let's just look at a very trivial example. Suppose we just have one dependent and one independent and one dependent variable. Then I can just think of a section as a function of x. So here's two functions of x. And if I calculate the partial derivatives at x equals 0, then I see that these two sections have the same derivatives at x equal to 0 up to order 2, but different derivatives at the origin at order 3. So we would say that these two sections define the same point in the second jet bundle, but not in the third jet bundle. And the fundamental property of these jet spaces is that you have this sort of tautological lift. Anytime you have a local section, you can lift that section up. Anytime you have a section here, it lifts to a section here just by taking the jets. Okay. So some familiar examples. If we're studying curves in the plane, then the second jet space would look like independent variable, dependent variable, two first derivatives, and two second derivatives. If we're studying surfaces, parameterized given by u as a function of x and y, then our second jet space would contain two independent variables, one dependent variable, two first derivatives, and three second derivatives. We're going to talk about variational problems involving metrics. And so in that case, our bundle E could be viewed as the bundle of symmetric type 0, 2 tensors over M. We would, if we wanted to study metrics, we'd have to impose the condition. We'd have to cut out of this space here the points where the determinant of our metric was, or the determinant of our tensor was 0. And that would be the bundle of metrics over a manifold M. So in this business here, I'm not so much interested in studying a given metric on a manifold. I want to study the bundle of all metrics over a manifold. In this case, we can generalize our integral that we talked about before, the Gaussian curvature. We can think of the Pfaffian as being a function on the two, sorry, let me back that up. We can think of, in this setting here, we can think of the curvature tensor as a metric as being a map on the two jets of this bundle into rank type 1,3 tensors on the manifold. So for us, curvature tensors are functions on jet space. Let's skip this discussion here. So the most important property of this jet space right here, we have projection maps from one jet space to another, but by far and away the most important property of this jet space is that it has a contact, a privileged structure on it called the contact ideal. You can view this contact ideal either as a collection of one forms, so defining a Foffian system, or you can take the annihilator and think of it as a distribution. They call it often called the Cartan distribution. And the definition of this contact ideal in the abstract is very easy to give. It's the set of all differential forms on the space such that which annihilate the lifts of any given section. Okay? And so this contact ideal actually characterizes the lifts of sections. If we have an arbitrary map from a neighborhood of M into our jet space, then that section can be written as the jet, and this section in the jet space can be written as the lift of a section of E, if and only if the contact system is annihilated. And so going back to our examples, if we're looking at our jet space X, U, UV, U dot, V dot, and so on, then we have four contact forms: theta U, du minus U dot dx, theta V, dV minus V dot dx. And you can see right away that as soon as I interpret U as a function of X, that is to say, pull this back by a section, then U becomes a function of X, D of U becomes U dot dx, and this vanishes. So it's very easy to write down the local bases for all these different contact forms. The structure equations are as follows. This first contact form differentiates into the next order one. This contact form, you can just easily calculate its exterior derivative, is not a contact form at this order, but it's dx times the exterior derivative of this. And then on the slide here, I've got another example. And I kind of made an editorial comment here that these structure equations, the structure equations for these contact forms, are very important in variational calculus and lots of aspects of differential geometry. And so somehow these formulas for the structure equations for the contact ideal, they're on the top 10 list of important formulas in differential geometry, I think. Okay. Properties of the contact system. Well, you have the following basic, there's only two I really want to talk about. The basic property is if you have a map from our fibered manifold to itself, it could be to another fibered manifold, then maps of this kind automatically lift to maps in jet space, and that lift is unique. It's calculated algebraically or by algebraic operations and differentiation. You don't have to solve differential equations to do this lift. And so maps lift in such a way as to preserve the contact ideal. Vector fields on E lift. Okay. Conversely, if you have a map on the jet space and it preserves the contact ideal, then it's not difficult to show that this map on the K-jets was actually coming from a lift or a prolongation of a map on lower jet spaces. So this is often referred to, this kind of phenomenon is often referred to as Becklin's theorem. And it's possible, if you would like, to try and throw away the details of the contact system, the exact contact system, and just try and do an axiomatic development saying, I only need to work with Foffian systems, which have this property, and this property. But for us, these are the important properties that we have in our concrete case. Okay. Let's see, somehow I've here. Okay. Okay, so the next step after we've introduced finite jets is to make this passage to the infinite jet space. So I don't want to review the topology of how you construct the infinite jets. The key point here is what it means to have a differential form on the infinite jet space. And that's right here. So this is really all we really need to know, is that any form on the infinite jet space is really locally a form on some finite jet space, formally pulled back to the infinite jet space if you want. So forms, functions, forms, Lagrangians, conservation laws, anything we're going to be interested in on the neighborhood of every point looks like a function on some finite dimensional jet space. Something happens that's very interesting when we go to the infinite jet space. Here are my contact forms, du alpha, u alpha I dxi, du alpha I minus the second derivatives. Here are the structure equations now for the contact forms on jet space. Since I'm allowing I don't truncate the orders, something big happens. Namely, now the contact ideal is algebraically generated by the one forms. So anytime you have a Pfaffian system which is algebraically generated by the one forms, that's Frobenius theorem, or the one set of one forms are integrable. So now one of the big things we pick up now is that the contact ideal on the infinite jet space, we really shouldn't say integrable, but we can say it's sort of formally integrable. What happens is we do lose track of orders of things. We don't care what the order of our objects are. All we know is that they're locally finite. The annihilator of the contact system is something that's very familiar to everyone. It's the set of total vector fields on our space of independent variables, or these are just total derivatives. Because this goes on forever, and because the derivative, the coefficient of the first derivative is the second derivative, these objects are to be sort of viewed as formal vector fields, in the sense that you can't really talk about the flow of these total vector fields. Okay. So we're ready.
So I have a question.
Yeah.
So go ahead. Is it integrable or not? So is there like do these vector fields integrate to surfaces or not?
I would say not. Mm-hmm. So they're integrable, but if you try and write down the equation for the flow, it's sort of like d by d epsilon of u alpha I equals u alpha ij kind of thing. So the derivative, so it never closes up. You can't kind of write down a finite dimensional set of ODEs for calculating the flow. That's all I wanted to say.
Okay. Is it correct to say that you can't integrate this distribution in terms of local functions?
Well, I can certainly say that if di of f is, I'll come back to that in a minute, okay? That's going to show up later on. Okay. Okay, so here we are. We started off with our distribution. We created the infinite jet space. We created the contact system. The annihilator of that are total vector fields. And then we have one more thing going on for us. We can look at all the vector fields on the infinite jet space which project to zero. Okay. So we now have a splitting of the tangent space of the infinite jet bundle. It splits into these total vector fields, d by dxi, and the vertical vector fields. And the vertical vector fields are just field derivatives, are just these. And now our structure equations this is an integrable distribution. This is formally integrable. And the only bracket that's non-zero is the bracket between the total derivative operator and a partial derivative operator. Now, as always, anytime you have a direct sum decomposition of the tangent space, you now get a direct sum decomposition of the space of forms. And so our forms on the infinite jet space can always be decomposed into a direct sum of type RS forms, where R is the horizontal degree and S is the vertical degree. So a form is of type RS if it looks like this. This is the horizontal degree. These are spatial, space-time variables, if you would, and then wedges of the contact forms, or you can think of these as field variations. Then the next big step, very important, by virtue of these structure equations, or by virtue of the structure equations for the contact ideal, the exterior derivative splits. So the exterior derivative of form of type RS has two components in it, R plus 1S part, a horizontal part, and a vertical part. So we have then that D is equal to DH plus DV. And here are the structure equations for the DH. DH of a function is just the total derivative of the function. dv of a function is just sort of a variation of the function. It's du dv times contact forms. dh of dx is 0. dh of a contact form is the contact form of the next higher order. dv of dx is 0, and dv of the contact forms are 0. So right here, this is all the makings of our variational bicomplex. So I've written it out for us right here. Okay, so in summary, again, we start off with a space of dependent and independent variables. We make the infinite jet space. We have mappings and vector fields on E prolong. Every vector field prolongs, and it can be split into a total vector field, which is a total derivative operator, and a field variation called the evolutionary part. Our total vector fields look like this. Our forms decompose like this. And now we have this big picture. And this picture here represents this double complex. In the corner here, we have 0, 0 forms or functions. Here we increase horizontal degree, so we have just one forms on the base, but with coefficients depending upon jets. Two forms on the base with coefficients depending upon jets. And right in the corner here, we have n forms with coefficients depending on jets. This is the space of Lagrangians. So in the variational bicomplex, this corner is especially important to us. It's called the space of Lagrangians. Going upwards, we have contact forms squared, cubes of contact forms. Then we have a horizontal degree 1, vertical degree 1, horizontal degree 1, vertical degree 2, and so on. Our exterior derivative, as I said, splits. Take an exterior derivative here, it'll have a piece here and a piece here. Okay. But there's one more piece which is absolutely important to us, and it's called this I call it I parts. It's the integration by parts operator, and the integration by parts operator lives all along this edge over here, and it's a map which maps top degree forms, top forms of top horizontal degree, the forms of top to themselves. And it looks like an Euler-Lagrange operator, only in place of using derivatives, we use interior products. So if we were doing Euler-Lagrange, this would be partial derivative of the Lagrangian. Here I'm hooking in with these vertical vector fields. Okay, so this I parts is sort of like an Euler-Lagrange operator with partial derivatives replaced by Hooke. And this has some really amazing properties. One, it kills horizontal derivatives. Two, it squares to itself, so it's a projection operator. It's kind of strange to see a differential operator be a projection operator, but that's what happens. And two, this is a natural differential operator, so it commutes with itself. Okay. And so,
may I ask a question?
Sure.
Is there an easy way to see that this separator, the integration by parts operator, has the exact form of, or what do you
Has these properties?
no, not about properties, but about the way you write it down.
Yeah, so let's see. I think so. That's a good question. Let me think about that a little bit. So I think if you start with these properties, you're going to arrive at this formula.
Okay.
Well, I know, yeah, but I don't know how easy that is to prove.
Oh, thank you.
Okay. Okay. So let me, oops, what's happening here? What just happened? I think I went to some full screen mode, huh? Okay, so let's put it all together now. We have this big Euler-Lagrange complex. This is a big variational complex. And I've added into this the I parts operator at the end. And I've noted that if I have a function here, and if I have a function and dH of f is 0, then that function is locally constant. So that's adding in this piece right here. And most importantly, if I have a contact form, so if I have a form here and dH of that contact form is 0, then that form must be 0. So this really will drive a lot of the things that are going to happen. Okay, so now I take this edge complex. So I take this piece here, and then I come up this way. Right at this spot here, I basically have the divergence operator. That's dH of an n-1 form. That's the divergence operator. At this spot right here, I have the Euler-Lagrange operator. At this spot right here, I have the Helmholtz operators. And here I have higher order analogs of these Helmholtz operators, which I wouldn't say too much about. Okay, so I'm pretty much out of time for today. I'll just end by saying that, let me just do one last slide and we'll pick this up tomorrow, that the Euler-Lagrange complex is locally exact. That the dV exactness, the exactness of the vertical columns, it uses sort of usual de Rham homotopy operators. So this homotopy operator is some kind of line integral. T times, I'm not going to write it down. It's a line integral exactly like you see for the homotopy operator for the usual de Rham complex, but on the dependent variables and the jets. And the interior rows are also exact. Okay. Now something very strange happens. There's homotopy operators for the interior rows, but these homotopy operators are again local differential operators. No line integrals required. They're more or less algebraic, and they involve only interior products and total derivatives. So it's kind of a strange situation. You shouldn't say this, but you could say, well, this is a case where the inverse of a differential operator is another differential operator. That's a weird thing to say, but it's happening because this exterior derivative dH takes things from order K, forms of order K, jet order K, up to jet order K plus 1. There's also a very nice inductive argument that you get for the proving exactness. But one thing you lose control of, unless you're very careful when you use these homotopy operators, is you lose control of the orders. So for example, you could have some form in the middle of this bicomplex. dH of it could be 0. You know that locally it's dH of something, but this could have had small order, maybe order 2 or 3, and the thing that you hit it with using the homotopy operators would have much higher order. Again, you can work hard to control the orders, but I don't want to talk too much about that. So in conclusion, for today, I didn't quite get to some of the applications, but we'll do those tomorrow. At this point here, we have a very, very effective variational calculus. We have the bicomplex, we have splitting of the exterior derivative, we have prolongations of vector fields which allow us to work with symmetries. We have an invariant formula for the Euler-Lagrange operator. We have a characterization of the solution to the inverse problem of the calculus of variations. We have a whole host of commutator rules for how commutators of vector fields, commutators of all the operators in the bicomplex. As some of you know, I've been working for many years also doing software development, and all of this variational calculus is available to us inside of Maple, inside the differential geometry package, in a package called Jet Calculus. So I think that's I don't want to go over time. So, well, I have gone over time. I'll try not to go any more over time. So thank you very much for excellent questions and for putting up with scribbling on a tablet for my talk today. And I look forward to continuing our discussions tomorrow.
So, thank you very much. Are there any further questions?
You're talking about the Gaussian curvature as an illustration to Noether's theorem about first integrals of motion. I was wondering what the curvature itself was not an integral. What integral did you mean? Did you mean to integrate the curvature?
I want to integrate. So in 2D, I want to integrate the Gaussian curvature. Okay. And in higher dimensions, I want to generate what's called the total curvature. And that's given by taking the Pfaffian of the matrix of curvature 2 forms. And all I wanted to say was these are known by the Gauss-Bonnet theorem or the Chern-Gauss-Bonnet theorem. These are known to be deformation invariants. So if you vary that this integral does not depend upon the metric. It only depends upon the topology of the underlying space. So all I wanted to say was that these very familiar objects to us in differential geometry are examples of null Lagrangians. And one of the things I want to talk about tomorrow is to flip this around. Can we study deformation invariants of different geometric structures by looking for null Lagrangians?